I would now like to turn today's event over to Loran Lehman, Vice President of Marketing and Public Relations for ATIS. Loran, you have the floor.
Thank you, and welcome everybody to today's webinar. All cellular radio base stations require precise synchronization. Developments in technology and in topology, such as TDD, LTE, LTE Advanced, and small cells, puts new demands on networks and methods to deliver sync to meet stricter phase requirements. During this webinar, relevant topics will be examined to show how to meet these demands. I'm pleased to introduce today's moderator, Tim Pearson. Tim is a technology strategist for Sprint. In addition to a strategic role, Tim is also Sprint's principal technical representative to the MEF. He leads Sprint's synchronization strategy by participating in the development of international standards for packet synchronization in ITUT Study Group 15, Question 13, and participates as Sprint's representative to ATIS's COAST Committee. And with that, Tim, the floor is yours.
Thank you, Lauren. Let's review our presenters today. First, we have Tim Frost. He's a Strategic Marketing Manager for Calnex. He has several years of experience in next-generation synchronization techniques, having worked with both Symmetricom and Xilinx Semiconductor on packet synchronization technologies. We also have Jim Olson. He's the Director of North American Solutions Architecture for Microsemi and has been with the company for over 30 years. Jim has served in a wide range of service, sales, and marketing and has extensive experience in design and implementing network synchronization and timing architecture in more than 50 countries. Tim and Jim, thanks for joining us today. Before we get started here, we're going to review really the provider's viewpoint, implications of using GPS for LTE E-Node B synchronization. We're going to review base station backhaul use cases, namely macro, indoor, and outdoor small cells, synchronization landscape, and further GPS-related challenges for backhaul providers as well as service providers. Base station backhaul use cases, service providers are deploying cost-effective all-carrier Ethernet mobile backhaul circuits for LTE base stations. They consist of both macro and small cell. The macros use environmental controlled cabinets that range from anywhere -40 to 55 degrees Celsius. They do have heaters primarily used for humidity control and forced air for cooling support. The small cells, indoor and outdoor, are made up of essentially micro, which is less than 2 kilometers, pico, less than 200 meters, and femto or eFemto, enterprise femto, which is less than 10 meters. Carrier Ethernet falls into two major categories for this backhaul. Fiber Ethernet, which can use multiple different types of protocols, essentially point-to-point and point-to-multipoint are being used today. Microwave Ethernet solutions are also being used. United States service providers are not going to abandon GPS as the primary distribution of frequency, phase, and time, but PTP, Precision Timing Protocol, remains an option for those, extending synchronization distribution at the edge, potentially even in building, and potentially possible redundancy of GPS. The macro use cases are quite simple. We have those interested or understand LTE. We have the evolved core, packet core, and has a primarily different types of service gateways that provide access to the internet. Again, we talk about the carrier Ethernet backhaul, but that could be owned or leased. And then we have the circuit providing that end-to-end connectivity to the site aggregating router. And here we have a GPS antenna providing that sole source of synchronization at the macro. The LTE indoor small use case, again, we have that same evolved packet core, but we've added a couple other things here because of the concern around the physical security of the small cells at the enterprise location. And here we have a security gateway as well as a small cell firewall providing that end-to-end solution for that IPsec interface between the small cell tunnel and the small cell gateway to the security gateway. Here we have the synchronization is provided by the GPS at the antenna rooftop, and it goes to the telecom Grand Master located here in this picture on the first floor. We have then a PTP signal coming from that Grand Master that's distributed to all the small cells via the site aggregating router. Again, these circuits between the enterprise gate, or excuse me, the involved packet core and the enterprises could be leased or owned by the service provider. This is really a phase one approach. Phase two is being looked at right now, but this is kind of cherry picking those required locations of density, if you will, for the urban environments. Here we have everything the same other than the fact that we have a GPS sole source synchronization. The landscape for the synchronization, again, we have the microcells that can be either FDD or TDD, and small cells, FDD, TDD. Again, the primary source here is GPS. High-level holdover times, and they differ between FDD and TDD, could be as high as 72 hours, specifically for FDD, and as high as 24 hours, again, for FDD. As we get into TDD, we'll explain later here, it gets a little more difficult to keep the phase for that time frame. The oscillator types are all crystal-based oscillators, which is a piezoelectric resonator, which does have the challenges. We'll talk about that here in a moment. Some general synchronization statements. One, UTC time is distributed using GPS in the U.S. GPS vulnerability and lack of redundancy may be a major issue for wireless providers. Those are being studied right now. For prolonged GPS outages, prolonged being 24-hour in this case, frequency is easy to meet for frequency division duplex or FDD and CDMA. Phase is harder to maintain for macro time TDD as well as CDMA, and even harder for those small cells. Most base stations use crystal-based oscillators. Some recent activity I want to point out to is ATIS has recommended that the United States Department of Homeland Security perform further study on vulnerability of current communication systems and threat scenarios. And finally, we'll review here the GPS-related challenges. A lot of people don't really realize that these crystal-based oscillators, the basis for those are piezoelectric resonators, and these devices change in pressure, and it's no different for temperature pressure. Now, business models dictate that small cells are low cost. This translates into low-cost components and therefore translates into low-cost oscillators. Crystal-based oscillators suffer from small temperature fluctuations greater than plus or minus 1 degree Celsius. Using PTP over GPS as a substitution or redundancy has security implications. Using IPsec poses a major issue for supporting PTP over the access network. An alternative solution to IPsec, which offers a deterministic authentication and encryption security, is needed, or you simply have PTP run outside the IPsec tunnel. There's an argument for that. PDD essentially is a PTP killer. Location, this is very important for North America. Emergency 911 remains a major challenge. Increased dependencies on small cells are causing providers to consider innovative methods of providing synchronization and location of the user of that small cell. Providers are looking for a plug-and-play synchronization and location solutions for small cells without GPS line of sight. Those might be urban site canyons for PICOs, as well as home and enterprise eFemtos. So I want to go ahead and introduce Tim Frost. Tim's going to review the LTE synchronization standard-based methods.
Thank you very much, Tim, and welcome everybody. So it's really good to get the service provider's viewpoint, as Tim Pearson has just outlined, and that forms the basis for everything we want to do here. So I'm going to talk a little bit about the synchronization methods that are being put forward by bodies like ITU, and also the requirements that are coming from bodies like 3GPP. So let's look at the 3GPP requirements to start with. Just waiting for the slide to come up here. Tim, if the slide's not advancing, can you push it on for me, please?
Yes, it's advanced, Tim.
Okay, just haven't caught up with me here. Okay, so 3GPP requirements originally was 50 parts per billion for technologies like LTE STD, and that's the same as going back to GSM and requirements before that. For TDD, we're talking about an additional requirement of 1.5 microseconds. Now, actually, if you read the 3GPP spec, that's not 1.5 microseconds, it's actually 3 microseconds. But that's phase difference between two adjacent base stations. So the way we supply this is to supply time synchronization from a central point, such that no base station is more than 1.5 microseconds away from that central point. When we go on to LTE-A, then we're talking about time synchronization requirements for the various different LTE-A features between 1 and 5 microseconds. And the reason why there's no hard number is because there's no hard number where these techniques stop working. It's a trade-off. You trade off whether you want enhanced throughput or enhanced performance versus how tight do you have to make the synchronization. So there's no point at which they stop working. So you could say, well, you need 1 microsecond for coordination requirements for small cells, for example. But then somebody else will say, well, actually, it will still work at 5 microseconds. You might not get quite as good a performance, but it's a trade-off. And then for small cells, we start needing, you have a slightly less requirement on the frequency, but you start needing things like, you still need the time synchronization requirements for things like TDD or EIC-IC. So how do we address those? Well, the ITU have come up with 2 basic methods that they're standardizing. The first one, we've just finished a standardization on at the last meeting. It's called PTP with full timing support. So that's the profile for that is in a document called G.8275.1. And basically what that does is you get your time synchronization from GPS. And that goes into a PRTC, which is basically the GPS receiver. And then you have a PTP grandmaster that's sending that through the network. And every point in the network has a boundary clock. So every switch or router on the path between the grandmaster and the slave has a boundary clock contained within it. And that boundary clock's function is to terminate the PTP protocol, regenerate the clock, and then pass it on. So it kind of cleans it up. It's acting like an EEC, Ethernet equipment clock, or an SDC, Sonic SDH equipment clock used to in the traditional sync network. Downside is, of course, that you need one at every node. Now, some of the benefits of the system, though, are that you get a really good, you have really good deterministic synchronization at each point. You've got a building block approach to network construction. You can look at just building up the network in a very deterministic fashion, and you know exactly what's going to happen to the performance each time you add a new block into it. And as I said earlier, the profile, the architecture, and the clock performance has been defined by ITUT and has just been agreed. The downside is the challenges are that all equipment needs to be PTP aware. And the last one is there's no control of asymmetry in the network. Asymmetry is the big problem. asymmetry is because PTP fundamentally cannot tell the difference if the path in the forward direction is longer than the path in the reverse direction. And that difference in length will cause an error. That's what we call the asymmetry problem. There's no control of asymmetry in this kind of network. You have to engineer that. So what's the budget then? So if we make up our 1.5 microsecond budget, we make it up from 100 nanoseconds from PRTC and the Grandmaster. We have 200 nanoseconds from random network variation. That's a noise that you accumulate going through the network. You might have several hundred nanoseconds from asymmetry, as I've just described. And there's two sorts of asymmetry. There's node asymmetry. That's error that each component introduces into the path. And there's also link asymmetry, which comes from the fact that the fiber lengths may be different between each node. You know, a forward fiber may be a different fiber to the reverse fiber. You may have added cuts or splices into that network, which results in a length difference. And that can all introduce time error. So our whole network equipment budget is actually 1.1 microsecond. And then we allow 250 nanoseconds for a short-term holdover and 150 nanoseconds for the end application. So that builds up a full 1.5 microsecond budget. Now then, the problem, as I said with that, is all equipment needs to be PTP aware. So we have this second method that's being under study in ITU at the moment, which is what we call PTP with assisted partial timing support. Now, certainly in North America, the operators have always had the advantage that most macro base stations in North America have GPS already at the base station. And that's because they've been using CDMA technologies that have always required time sync. That's different in Europe, where operators have had GSM networks where they haven't needed time synchronization. But the object here then is to back up that GPS. What happens if the GPS is jammed in some way? What happens if we have a hurricane and the GPS antenna is knocked out? We need some method of backing up GPS such that we have time to go out to the base station and fix the antenna up again, or that it can ride out any jamming problems. So the object is using PTP to back up GPS. Now you'll see here also in the network diagram, many of the switches and routers do not have boundary clocks in them. And that's because we need this technology to work over existing networks. We may not be able to replace every node in the network. So the benefits of this system is that it's a symbiotic relationship between PTP and GPS. There's mutual cooperation between them. So, for example, PTP can provide an initial time fix, which helps GPS signal acquisition, particularly in low signal areas. The GPS can calibrate the PTP asymmetry and monitor its suitability for the service. And the PTP itself can monitor GPS timing quality. It might be able to tell you when you have issues such as antenna failure or spoofing and jamming. It's going to operate over existing networks, including, say, third-party access networks that might not have PTP support. And the profile, the architecture, and clock performance are still under definition in ITU. It's planned for consent in December this year, but it may well extend into next year. Challenges are, it's a less deterministic path from the Grandmaster to the assisted partial timing support clock, because not every network element assists in the timing flow. So we may need to provide constraints on the traffic load and the span of the network. So if we look at the budget for this one, I've removed now the constant time error that we had from the full timing support, and we replace that with what we call the GPS calibration uncertainty. So that's the difference between the two GPS engines at the source of a PTP and also the GPS engine at the base station. And that leaves us a whole lot more room for the random network variation. So we can get up to 800 nanoseconds for random network variation now. But we'll need that because the noise accumulation through the network is much greater than it was before. So, is PTP working then? How do we know that if we look at the endpoints, either the input to the slave or the output from the base station, how do we know that that's going to be working? Well, fundamentally, you always need a time reference to measure time. Otherwise, you have no idea. So you need an accurate time measurement, time reference, and normally for field measurements, that needs a GPS engine. So if we have a GPS engine connected to our test equipment, then we can look at the sort of measurements we need, whether that's looking at the PDV or looking at the output of the clock, and we can then tell whether the PTP is actually working. But fundamentally, unless we have that time reference to compare to, we don't really know if it's working or not. So fault finding then, if something stopped working, we don't know why, we could take an instrument out to the field, connect it up to GPS, and then we can measure the PDV through the network, and we can capture that, and we might be able to take that back to the lab and then apply that in a lab setting, that measured, captured PDV, and see whether the actual master clocks and slave clocks are talking together properly, and whether they're, with that level of PDV, whether they're able to maintain synchronization or not. So it gives us some ability to fault find the equipment. So in summary then, ITU is specifying two ways to support distribution of time and phase using PTP. Full timing support is a good method, but it's vulnerable to asymmetry. Partial timing support is vulnerable to PDV. So GPS is still the best source of time and phase out there. And as Tim said earlier, North American operators are certainly not going to move away from GPS as their primary source of time and phase. But assisted partial timing support is a way of combining the benefits of both GPS and PTP. And testing and fault finding require an accurate time reference, and typically that also comes from GPS. So we're not going to throw away GPS anytime soon. All right, thank you.
Thank you so much, Tim. I appreciate that. We want to now move to Jim Olson. Jim Olson is the Director of North America Solutions Architecture for Microsemi. Jim, the floor is yours.
Thank you, Tim, and good morning, everyone. First, I'd like to thank my co-presenters, Tim Pearson and Tim Frost, and of course, ADAS for sponsoring the webinar. Slide showing is the agenda for my portion of the presentation. We're going to talk about setting UTC traceable time and phase into the LTE small cell architecture, and then how do you maintain this time and phase once it has been set, and the third component, which is holding time and phase if the mechanisms to set and maintain time and phase are no longer available. So first, setting UTC traceable time and phase in the network, what are the technologies available to us to perform this function? So there are a couple technologies available, and the reason we're deploying them is the drivers for UTC time and phase. LTE advanced features require interference mitigation. EICIC, COMP are examples of overlay technologies for LTE advanced features that require very tight coordination. Also, LTE time division duplex also has very tight phase requirements. And again, how do we deliver time and phase to meet these requirements? We have two technologies available, the first being GPS, and here are some of the advantages and disadvantages of GPS. Typically, GPS provides very good accuracy, better than 100 nanoseconds, traceable to UTC time. It's available around the globe, but it does need line of sight and clear view of the satellites. It also provides a component, latitude, longitude, height, the position required to support E911 requirements here in the U.S. markets. There are some disadvantages to GPS. Urban canyons cause line-of-sight issues. GPS can also be vulnerable to things like jamming, spoofing, and unintentional interference. Also, GPS antennas, for various reasons, can fail. They are not bulletproof or foolproof. You also have a cost associated with GPS of maintaining the antennas, cables. Also, installation costs associated with this can be fairly high in metro urban environments. The other technology we have available in our toolkit is PTP, or IEEE 1588. It does have some advantages, particularly for indoor applications. It is much more practical to use PTP in an indoor environment than try to cable GPS to multiple cells in an indoor ecosystem. You can also put very good holdover capability in the grandmaster clocks. If the GPS fails, for example, you can put atomic clock or video oscillator holdover if the cost is warranted, which will hold phase much better than the crystal oscillators Tim Pearson was describing in his presentation. PTP is also a network-based service. As long as the network's up, typically PTP is available. There are some disadvantages. Both Tim Pearson and Tim Frost talked about PTP and the enemies of PTP being asymmetry and PDV. They do limit the reach of how long we can extend a chain through switches and routers to enable PTP. Also a disadvantage, no positioning information is available with PTP, and as Tim Pearson indicated, if PTP is going to be a primary mechanism for delivering time and phase into a small cell architecture, how do we solve the positioning piece for E911 requirements here in the U.S.? In addition, how does security such as IPsec impact PTP flows? I think this is a subject that needs to be studied further to find out what is the impact and what can we do to position PTP and make it work effectively in that environment. So when we talk about using PTP for time transfer, there are three potential sources of error for time transfer: the grandmaster clock itself, the network, and also the PTP client itself. So first, source of error, the grandmaster clock. What is the solution to fix that? Is what Tim Frost was saying, or described as the PRTC, or a primary reference time clock. What is a primary reference time clock? It comes from the ITU standard G.8272. And a primary reference time clock is a grandmaster that always stays within 100 nanoseconds of GPS UTC traceable time. So Tim talked about error budgets, and this means that PRTC function means the grandmaster always stays within its allocated error budget. An interesting component of this is UTC traceable time is required to mitigate interference. Arbitrary phase coming from a frequency reference or something that is not traceable to UTC time is not adequate for these applications. Because if we have a situation where we're overlapping base stations, where some are using arbitrary phase and some are using UTC's traceable time in phase, this will result in interference coordination issues. So all these PTP-based devices used in this architecture need to be UTC traceable. So the next source of error would be the network itself. And both Tim Pearson and Tim Frost indicated the problems with a time transfer in the network being asymmetry and PDV. Tim Frost described what asymmetry is and why it is problematic, and the models associated with the solutions to asymmetry and PDV. One being G.8275.1, which is ratified in the ITU, and that is the full timing path support model. There are other models and contributions being made, such as partial timing support and assisted partial timing support. We'll talk more about assisted partial timing support in a minute. The third component of time transfer error lies within the client itself. So a client PTP design in an eNode B, whether it be a macro or small cell, must be designed within the error budgets that were specified in Tim Frost's presentation. If you're going to design a small cell or an eNode B, you must design within this error budget when using a PTP client of 150 nanoseconds. In some cases, I think most cells will meet this, but not guaranteed, especially when you couple it with the crystal oscillators Tim Pearson was talking about in the design, as that is an important component of the design and may be the most critical single factor to determine whether that design meets the error budget or not. PTP clients within the error budget of 150 nanoseconds include both the end eNode B small cell or macro cell itself, as well as anything in the PTP chain that has a PTP client in it. Boundary clocks have PTP clients in them. They are a slave on one side and a grandmaster on the other side. So this design of the boundary clocks, as we talked about within the error budget, also has a fixed error budget and must be designed to meet that as well. If you look at G.8271, which is also an ITU standard, it calls for a 1 pulse per second output from all client devices or any device that is used in this error budget end-to-end network model. So whether it's a boundary clock or a client or a grandmaster, if we are going to test these devices to see how much of the error budget they're consuming, whether it's a grandmaster, whether it's a boundary clock in the network, whether it's an end device, without a 1 pulse per second available output on these devices, it's very difficult to figure out if you're consuming more or less than the error budget you are allocated. So I would encourage all the vendors making products into this ecosystem to provide a 1 PPS output so that whether it's a laboratory environment or a live network, these error budget calculations can be made, measured, to determine whether they're meeting the requirements or not. So next is maintaining UTC traceable time and phase. Once we have set time and phase into a base station or an eNode B, it's much more easy to maintain it. And GPS will maintain time and phase automatically when it updates GPS. PTP Grandmaster clocks using GPS will also update and maintain phase once it has been set. One of the important points to remember here, though, as Tim Frost mentioned, assisted partial timing support. This has a built-in asymmetry compensation technology available to us. If we have GPS on both locations where we're generating PTP and receiving PTP, we can take a very accurate one-way delay measurement and compensate for any asymmetry that may be in the path between those two devices. In this case, GPS and PTP are complementary. As Tim Frost said, PTP can help GPS acquire satellites faster, track faster, etc. GPS in these devices at the endpoints can also measure asymmetry and compensate for asymmetry, so they're very complementary. I would challenge the operators in the LTE ecosystem to challenge the vendors to move towards a more robust ecosystem that includes both GPS and PTP. This does not add any significant cost to the ecosystem and addresses the shortcomings of both GPS and PTP. So the next topic here is holdover. So maintaining time and phase is not the same as holding time and phase or entering into a holdover mode of operation. If the method used to set or maintain time and phase becomes unavailable, you will then go into holdover or hold time and phase based on the accuracy of the internal oscillator in the eNode B or small cell itself. As Tim Frost said, these oscillators used in these cells are very cheap oscillators. And there's a reason for that, because the business case is pushing towards eliminating the cost of expensive oscillators. So for some reason, we lose the source of GPS or PTP becomes unavailable. This cell with these cheap oscillators should be removed from service very quickly, as it becomes a source of interference within just a few minutes. There are other holdover mechanisms related to frequency references that can also hold phase. For example, a Grandmaster clock with a rubidium atomic oscillator in it will hold frequency for many months for the requirements for a base station, but it will also hold time and phase very accurately for maybe 24 to 48 hours within 1 microsecond. Also, a stratum 1 or G.811 level of frequency accuracy reference, such as you get from an atomic clock cesium standard, can also be used to back up Grandmaster clocks in the event of a GPS failure. And these types of accuracies you get from a stratum 1 device, which could be GPS, it could be a cesium-based device, will hold frequency for a very long time, but will also hold phase for up to 5 to 10 days. So the holdover mechanisms are available, and one of them is a technology called Synchronous Ethernet. Synchronous Ethernet is used to distribute frequency within a network. It cannot be used for setting time and phase, but it can be used to distribute frequency. If the synchronization Ethernet reference is accurate enough, if it is traceable back to stratum 1 G.811 accuracy, it could also be used to hold phase very accurately in a base station in the event PTP or GPS is no longer available. But that synchronous Ethernet reference must be extremely accurate and referenced back to UTC traceable time and phase, which would be a GPS-based frequency reference or a cesium atomic clock. So watch out in the networks for synchronous Ethernet, because it's becoming available in a lot of places, but make sure it is traceable to an accurate reference, or it will be of no benefit to you in a time and phase environment that requires holdover. So this concludes my portion of the presentation. Thank you for attending the webinar, and back to the moderator.
Thanks, Jim. We're going to now talk about the questions. We'll have a few questions that have been posted. We appreciate those who've posted the questions. This question is a twofold question, and the questions seem to be around GPS. So the question is, GPS provides position for 911. Can this be supplied at the small cell installation? And so I'll start with this, and then maybe, Jim, we can also kind of get your input on this as well. The problem with that is that, in fact, if it's in an enterprise location, you're looking at extensive GPS repeater sources to all your small cells, and then you have run into the problem of the GPS is really just getting the location of the antenna, so it really doesn't help you. It helps you in XY coordinates, but it does not help you in Z coordinates. So it's your emergency team is going to respond to the antenna itself upon a call. So that really doesn't help. And Jim, do you have anything to add on that?
Yeah, Tim, I think that's a correct assessment. This is a pretty big problem for indoor applications because, as you said, you're transferring the position of the antenna, really not the receiver. So if the receiver is in close proximity to the cells, you're still not necessarily solving the problem. There are some interesting technologies out there that are associated with sniffing technologies that can sniff out signals from macro stations in close proximity to where a small cell architecture might be, and using these technologies along with what we already have available for rudimentary positioning from the GPS antenna itself, combining these technologies may solve that equation. And I think There are companies in the industry working on these types of solutions. I don't think it is a fully cooked meal yet, but stay tuned as this is a problem that must be solved.
Yeah, we talked about that before. The service providers want a plug-and-play situation. And so there's other options such as just dynamically putting, essentially just putting the location in the small cell itself. That runs into a problem, obviously, because it's a longer installation, and then if somebody picks that Pico up and moves it to another location, again, you're going to be sending the responders to another location. So, Tim, the next question is back to you, Tim Frost. How different is the scenario from the full BC network to the assisted partial timing support? I think you covered that, but maybe just a little bit more detail in regards to how it's implemented, how it might be implemented here in the United States.
I think the full BC network is really a greenfield site. If you can start from scratch, that's how you do it. But it's very difficult to retrofit that to an existing network, and that's why we're looking at the partial timing support and assisting GPS. That's really all about what can we do over existing networks.
Very good. Now, let me add something to that, Tim. From an access perspective, Sprint deploys these eNode Bs, and we're very reliant on our access partners. The same thing with T-Mobile. They're also relying on our access providers. And the other side, the Verizon and AT&T aren't everywhere. They, too, rely on other access providers outside their territory. So a different approach so that you're not depending upon solely your access providers and putting a boundary clock at every node would be very helpful. So the next question is a general question. What's the perspective of timing for 5G technologies to come? I'll just briefly say, from my understanding with 3GPP and where they're at with 5G technology discussions, really the synchronization hasn't been worked out and is not nailed down yet. Will that tighten? I don't know. It will require additional phase requirements beyond 1.5 from a macro perspective, TD. I don't know. Tim, have you heard anything in the small cell forum that you're involved with?
I don't really know what 5G technologies are going to bring. What's going to be different about that? I can't see it's going to be much different because it's very difficult to get much tighter than we're already shooting for.
Very good. This is another follow-up question on small cells, Tim, so maybe I address it to you. What about small cell intercell synchronization using sniffer, i.e. over the air from a macro?
That's certainly a technology that's being used and implemented. I think for small cells themselves, then there's going to be a whole smorgasbord of techniques. It's not just going to be PTP, it's not going to be GPS, it's not just going to be sniffing. They all have their place, and sniffing is certainly one of them, and it certainly does get used in some places, but for every technology you can think of, there's a downside, and that's why you need a whole range of different techniques.
Okay, this is a follow-up, or actually not a follow-up, Tim, but I think this might be good for you. Can you discuss the difference between BCs in each Ethernet node and TCs, that's transparent clocks, in the intermediate nodes?
Yeah, so a BC is a boundary clock. It recovers the timing and terminates it, and then sends on a new timing stream. The TC processes the timing stream and sends a correction factor. There's advantages of each. I think the BC one is what's been chosen for full timing support profile, although the TC would equally well have worked. It's just we wanted to focus on one rather than trying to make the problem too big by allowing so many different options. But certainly TC is something that's being used in a lot of access technologies. particularly microwave, for example. Microwave vendors are putting TCs in there and treating the whole microwave system as a big transparent clock, and that's very applicable for that kind of technology. So I think in actual deployment you'll see a mix of both, and it will, again, it depend on what sort of system you're putting in, might depend on geographical reasons or particular access technologies that you're using. Thanks,
Tim. Jim, this might be directed towards you, and you've done a lot of field work, obviously, with over 50 countries of access involvement with your synchronization rollouts. This question comes for those recently new Ethernet access nodes. The question is, will, say, recent carrier Ethernet nodes in backhaul upgrade to support boundary clocks by, say, a software upgrade as opposed to a hardware upgrade?
Repeat the question, Tim. I'm not sure I understand the question.
Okay, I'll repeat the question. I think I understand what they're trying to say here. Will, say, recent carrier Ethernet nodes, in other words, carrier nodes that have just been installed in backhaul, can we upgrade those to support boundary clocks by a software upgrade as opposed to a hardware upgrade? In other words, a forklift, if you will.
Yeah, that's a good question, and I think that depends on how robust of a solution you want. You could upgrade existing routers or switches in the network to support boundary clock functions, but typically Synchronous Ethernet and PTP boundary clock functions go hand in hand. There is a distinct advantage using an accurate frequency reference from Synchronous Ethernet to enable boundary clock functions. If you do this, it would require an upgrade normally of the oscillators inside the routers or switches themselves from 100 part per million free-running clocks to 4.6 part per million oscillators inside the devices. So if you really want to attack the problem in a robust fashion to make sure you're addressing PDV and asymmetry mitigation, you would want to apply that SYNC reference. And so that just a software upgrade would not be sufficient. You would have to forklift the oscillators and whatever other, components or pieces of the fabric to support the Synchronous Ethernet deployment.
Very good, Jim. I'm going to ask another question for you, Jim. Can you talk briefly about the use of local clocks for holdover, and really how realistic are they for service providers?
That's a good question, and if you're using PTP as a primary source of timing for these applications, holdover is important. And holdover is important in both the grandmaster clock and any of the devices in the chain. For example, a boundary clock chain. If you lose the PTP feed to a boundary clock and that last device in the chain enters holdover, what type of holdover are you getting? If it's a cheap crystal oscillator, you only have minutes to support phase. How do you address that? One way to address that would be Synchronous Ethernet, which again would have to be traceable back to a Stratum 1 source. And if we lose our source like GPS at that location, rubidium atomic clock oscillator holdover for the Synchronous Ethernet chain or the PTP flow would be highly recommended. So it's an architecture question as well. I wouldn't want to go into holdover on just a cheap crystal oscillator at the end of a timing chain. I would engineer the network to avoid that.
Very good, Jim. This is going to be directed to Tim Frost. Tim, you've done a lot of work in China and the eastern side there, as well as Europe. There are fully deployed, full on-path support networks out there, and obviously some of those have the major issue, as you talked about, is the asymmetry. And this question really is, what options are there for those networks to control that asymmetry that you talked about that's very dangerous?
So typically what a lot of the Chinese companies are doing is they're having to manually measure the asymmetry and then plug that in as a compensation factor. And that involves measuring delay through fibers, basically. So it's a very manual, intensive process, and I would say it's error-prone as well. It's not the easiest process to handle. The best way to control it, really, is to make the links as short as possible and to put the GPS system as far out towards the edge of the network as you can. And that will minimize the asymmetry to the point where it's not a problem. But if you have a very big, deep, centralized system, then you're always going to be vulnerable to this.
Okay, thank you so much, Tim. This question here just recently posted, GPS or GNSS setup. So this is the GPS is specifically a United States satellite system. GNSS is a universal standardized system name. Here in the United States, we use GPS. The question is, I think maybe could go to Jim. Jim, are we also using other systems, GNSS, here in the United States?
Yes, Tim, we are. Typically, the new receiver designs allow options for just GPS or adding GNSS functions, so that for some reason we're not able to track GPS, for example, it's jammed or interfered with, and maybe or maybe not the GNSS is still available. We can utilize that in some sort of failure scenario, and that could also be applicable to the GPS satellite system itself. Maybe there may be some testing going on or unavailability for a certain amount of times where we can fall back to the other signals available with GNSS.
Okay, so maybe even just the final question here, it looks like if we don't get another one posted, are there other signals, are there other sources of timing available to us other than, say, for instance, GPS, GNSS, or PTP for that matter?
Yeah, this is Jim, and Tim, I think, there used to be a lot of availability. In the U.S., we had Loran, which was available to distribute both frequency and time, but they've turned that down. There's some talk about whether they will utilize that again in the future, but it's currently no longer available. Network Time Protocol, or NTP, has been used for frequency in some eNode B applications, but NTP is very difficult to deliver time and phase, as the number of samples just does not support the accurate delivery of time and phase. So really, today GPS, PTP are the two main technologies available. I don't see anything realistically other than that, other than potentially some of the things we talked about with sniffing technologies. Other than that, I don't see anything emerging.
Very good, Jim. I appreciate it. Tim Frost, thank you so much for joining us, as well as Jim Olson. For more information about synchronization issues, please join us at the 2014 NIST ATIS workshop on synchronization in telecom systems. That's June 9th through the 12th in San Jose, California. To register for the tutorial on Monday afternoon, or you can register for the tutorial as well as the workshop, please register at the website is www.atis.org/WSTS.
Thank you, Tim, and to all of our presenters. On behalf of ATIS, I appreciate everyone attending today's webinar. The presentation will be available online, and slides will be distributed to all participants as well. Thank you, and have a great day.